Now, before we talk about neural networks, we will first talk about our good old linear and logistic regression, and we will actually see how we can interpret those as simple neurons, which then by stacking them together will be forming our neural networks. This is why it was important to focus on those techniques a bit more last week, as they just keep on popping up again, and you can't really understand neural networks unless you have understood linear and logistic regression first. So just a very, very brief recap. I do not want to spend too much time on it, but just to recall that in least squares regression, we just had a kind of a function, which was a linear function in my predictors, and it gave out a continuous variable because my response variable was continuous. In this case, I had p predictors and I had an intercept, and in principle I could have kind of n observations here where I goes from 1 to n, and the idea was to kind of minimize some form of loss, which was this kind of least squares, which because we had a square loss here, which we also motivated using maximum likelihood estimation. Now we knew that it is much easier if we kind of write this previous model in vector notation, and this is generally the case here as well. When we're talking about neural networks later on, it's very useful to write everything in a vector notation, where here we introduced this model matrix last week, which is just a matrix which has ones in the first column and then each predictor in the subsequent column, or each observations from individual predictors in the subsequent columns. This just helps the math, because now I don't have to worry about the intercept separately. I can just write this equation here for all I in this simple form, which is just a matrix vector product. So this was just to recap what we did in linear regression last week. But it's interesting to see that we can kind of view this linear regression model as a form of computational graph. And now this idea of computational graph is quite important, and it's heavily used later when we talk about TensorFlow. And the nice thing is that that computational graphs, you can look it up on Wikipedia, because I can't cover all the details, but it's something really interesting from a computational point of view, because on these graphs I can have something which is called automatic differentiation, so I can easily find derivatives. And this is just to give you some head-ups why those computational graphs will be good, and maybe put things into context if you've already heard about them. But let's just start at the basics and see how they come about. So the basic idea is, let's take this matrix X here. We call this matrix X was just a matrix which has kind of p+1 columns here and n rows. And let's just kind of think about rather than kind of processing observation by observation, running through these lines effectively, I can think of pushing them like through a graph, which is a bit like pipes, so the information flows through it. And what I'm doing is, to do so, I kind of rotating this matrix by 90 degrees. So now I have this thing, so this is why I said transpose here. So I have n observations here. So now each row in the previous matrix becomes a column here, basically. And here I have the p+1 rows here, which are just the intercept, and then the value for each predictor. And I can think of it basically, each kind of column in this data now flows into the graph. So kind of this element comes and it kind of flows through here. This element comes and it flows through here, and so on. All the elements flow through the graph. Then they arrive at the node, they get added up, and kind of out comes the sum here, which is just a function f of x. And kind of on the way, I just forgot to mention that they get multiplied by this factor here. So I get this value, x0, I multiply it by a0, and then I add it up. Now I get x1 multiplied by a1, and I add it up. And then I get this function f of x, which in matrix notation is just x times a. So this is the basic idea behind the computational graphs. I just view the kind of flow of information. So far, it shouldn't be much of a kind of new addition here. I think it just helps to think about it in this way. So I have this kind of my data frame, and if I rotate it, I have kind of columns coming in. I kind of push them through by multiplying effectively each of the elements here by a. So if you like, this a0, a1 up to ap is a p plus 1 dimensional vector, and this one is always multiplied with each of the columns, and then I kind of add them all up and process it. And the nice way is that I can also do all this vectorization, all these computations very easily in a vectorized manner. You will see that all these operations are very simple matrix vector or later matrix multiplication, and you can do them very efficiently in your computer. And there are kind of techniques to do them efficiently. There are packages. NumPy does that very efficiently. So if you write it in this way, you don't really have to worry about how to do it in the fastest way, because the software already knows how to do it in the best possible way. Now, this is for the standard least squares regression. The same holds true for logistic regression, because we know in logistic regression, all we do, we take kind of the same linear function, but rather than kind of spitting out the response variable f, we kind of rescale it to be between 0 and 1 and correspond to a probability by kind of putting it through the sigmoid function here. And so what we output in the case of logistic regression is not f, but we output s of f, which is just the sigmoid function of the linear function f, and we call the sigmoid function has this shape as is shown at the bottom there, this s-shaped function there. But now effectively my computational graph looks quite similar to before. Again, I have this matrix which had kind of all the n observations here, p plus n rows here, which corresponds to those variables here. Now I push it through the graph, observation by observation. Each time it gets multiplied by those coefficients a. Then I ending up effectively adding it all up here, but rather than kind of spitting it out directly, I'm having another process here. I could even write it as another circle. I could now effectively, after adding it up, I could pass it through the function s, and then I put out s of the sum basically. And this is exactly what I have written here. So this is just again a matrix which would be the function s of x of a, where if I write s of x of a, obviously x times x is a matrix, x times a is a vector, and s of x times a just means the vector where to each element I apply the function. So whenever I apply a function to a vector or a matrix, I'm meaning element-wise applications of that function, which is kind of the default way of using it in computer science. So this is now how you see how the kind of logistic regression works. Sorry, this is already logistic regression here. So we did the linear regression, now we do the logistic regression, where we just effectively push the data through the computational graph. All we do in comparison to the linear regression here is here we just directly spit out the value, the numerical value after adding this up. But what we do here is effectively, after we have done it, we just still squeeze it through this function s, and only after passing it through the function s do we kind of spit out the final value. But this is kind of how we can view the computational graph. So as I said earlier, this computational graph is quite important for computational reasons. It will allow us for automatic differentiation, which is really cool. I kind of recommend you to read up on it in your own time. You don't really have to know that for the matter of this course, but it's quite interesting to know about. It helps us to figure out how we can best view the kind of linear algebra behind it. I already mentioned we have a matrix, I multiply a vector, out comes again a vector, so we can kind of optimize this when implementing all these operations. We can do that in the best possible way, but also writing the graph gives us a very good interpretation of this model. In particular, we can interpret this, and it looks already a little bit like it, like a kind of neuron here. We see the neuron has this kind of a neuron in the body, has this kind of, this is a cell of the neuron here. It has this dendroids coming in, which effectively take on information from elsewhere, which could be coming from other neurons. In this case, information comes from the data, we take it on, we process it. In our case, we kind of added them all up, and we applied a squashing function, and then we effectively, here the neuron kind of gives out a signal. And often in neurons, there's kind of a threshold, so you have to overcome a certain threshold before the neuron fires its signal. And this can be sort of a little bit like this function, the sigmoid function. You can think of this shape of the sigmoid function here being effectively like a threshold, where you kind of effectively, if it's here, it's not firing, and if it's here, it's firing. So kind of depending on the value of the output, it would be not firing and firing. Obviously, there's this intermediate range, but this is just how this function works. But you could also make it steeper effectively, and we will see that in a second. So this is just the analogy between the kind of logistic regression and neurons, and it's exactly that analogy which we will be using to kind of build neural networks in a little bit. But I just wanted to see that a linear regression model, in a sense, is a very simplistic neural network. It's just a one-layer neural network, or a neural network with just one neuron, if you like so, but it is a very simple form of neural network. So a lot of the ideas which we apply later on for neural network, especially the training through kind of gradient descent and backpropagation, we can already discuss in the context of linear regression, which I want to do in a little bit. And this will actually help us to understand it much better before we go to the big neural networks, where it becomes a bit harder to understand. As a little side remark, I mean, this function as the sigmoid function is sometimes also called the activation function. And there are different activation functions. If you read in the neural network literature, you can see many people using different activation functions, and I just wanted to flash on some here. So this was a sigmoid function, but some other people like to use tanh functions, which looks quite similar. You think about similar looking functions here. This one is the only difference that rather than between 0 and 1, this one goes between 1 and -1, which can have some advantages in some cases. This is a ReLU, which is quite famous as well. The nice thing, it is 0 here and linear here. This can cause some nice computational efficiency in some cases, which is why you might want to use this one here. On the flip side, it does have this little kings here, and the kings can cause some issues potentially with kind of gradient descent here. Then you have this leaky ReLU, which has this thing which is not exactly 0 here, because if something is 0, it will sometimes cause flat region when we do gradient descent, and I can't find the optimizer, so I might want to kind of change this slightly. And then I have also some other ones which are less commonly used. The nice thing is that this ReLU is actually quite closely related to the hinge loss. We see it's exactly the hinge loss, just looked at from a different angle, which is something we already saw in the support vector machine lecture just yesterday, basically. So it's nice to see how things fit together. And this is just for you to give you some overview. And all it really does, if you hear some complicated thing of, well, we use this neural network with ReLU activation function, all it really means, like, okay, there are these little neurons which effectively like logistic regressions, and all they did is, rather than using the sigmoid function like we use in logistic regression, they used a different one which looks quite similar, but rather than being smooth, it is kinky. But this is the only difference. So hopefully you will see that much of the kind of fancy vocabulary, the words are quite fancy in the neural network kind of related areas there. It all sounds very kind of neuroscience related and very interesting names, but often behind the fancy names there's just some very basic idea which is just a kind of it's effectively an approximation to this loss function which we used previously. So it doesn't have to be so complicated, and I hope this helps you a little bit to navigate the literature. Now, what I promised, I wanted to quickly talk a little bit about how we can do learning, and I briefly kind of touched on it already earlier when we talked about linear regression. We had the kind of analytical solution, but I said in some cases we want to do gradient descent, and now kind of for the kind of linear regression, well, there was no reason necessarily, unless the problem is very big, as I mentioned, to do gradient descent. I can always find the solution, and especially I have this kind of, it's quadratic, as you can see here, and I have it's convex as well, I have a unique global minimum, so I can easily find a solution, and it will be a unique solution. We will see later that for neural networks it won't be so simple anymore. The optimization problem is kind of highly non-convex. It can look like this, and it's very difficult to kind of find a solution, and sometimes you might find this solution which is only a local minimum rather than, say, the global minimum. So there are some complexities, but let's just understand the simple case first. So as we discussed, our loss function, and let's just look at the simple case of least squares. We just have effectively, we square the difference between the actual output of and the output of our function f here basically, and we square it, and then we just sum it all up. And here we introduced a prefactor, a half here, and a prefactor of n. We didn't use this prefactor when we talked about linear regression last week. It doesn't really matter, because the optimization, when you find a minimum, it doesn't really matter whether you multiply the loss function by a factor, you just shift it up and down, but we'll still find the same optimum here. Here's just introduced for convenience. The factor of a half will just cancel the factor of 2, which you get down when differentiating. You will get down a factor of 2. So the factor of half is just introduced to cancel the factor of 2. That's why it's there basically. And this 1 over n is just because obviously then I can interpret the sum as an average. Now it's just 1 over n times. So I'm effectively calculating this, the kind of deviation from the least, so this kind of the squared residual here for each of the data points. And now, rather than saying I'm summing them up, I'm kind of averaging them. So without the 1 over n, it would be a sum. Now it's an average, basically. And what I'm doing now is I take this loss function, so Q is my loss function here, and I will differentiate it. And I can also see that I can kind of commute the differentiation operation with the sum. So that's the same as effectively, so the differentiation of the average of the residuals is the same as the average of the differentiation of the residuals here. So I can put the average outside and put the kind of the gradient inside. So I'm kind of calculating the gradient for each of these residuals and then averaging, or the other way around. It doesn't really matter. But the idea is that once I have calculated the gradient, I can now do gradient descent, whereby I say I have my weights and I start with some random choice of weights, and then I will update them to new weights, where I basically take the gradient and I'm going down with a minus sign in the direction of kind of steepest descent here. So I'm kind of going downhill like is shown here. I start with any random point, and now I'm effectively calculating the gradient here. I'm moving down, calculating a new gradient, moving down, and so on. So each step I'm doing an update from, say, omega 0 to omega 1 and so on. This would be the kind of weight space here. Omega, we called this omega as beta before, so just a slight change in, we called them A before, so I call it omega or A, it doesn't really matter, whatever those coefficients are here. So sorry for the kind of slight change in notation. Here we call them A, but A and omega are the same thing. I just happen to call them differently here in this slide. But this is just the coefficients of the coefficient I want to optimize for, which would be omega or A. Just kind of as a side remark, omega is the same as A here previously. And kind of now I'm going downhill until I find the optimum, and I have this other parameter here which is called the learning rate. It just tells me how fast I want to go in, and obviously if I choose it too small, I might find the solution, but it will take forever because I'm going kind of tiny steps, and it will take forever. But if I choose the learning rate too high, I might just be shooting like from one side to the other side, and I will just be doing like this, and I will never find the solution there. So it's important that you choose the reasonable learning rate, and again you can do some experiments there where you investigate and you can kind of do some cross-validation to find which is actually a good learning rate to use here. If the learning rate is too high, you will just kind of go around like a ping ball. You wouldn't find the solution. You will see that your test error is higher actually, whereas if you choose it low enough, then you will kind of find the best test error. And if you choose it too small and you want it for a fixed number of iterations, you might only end up here rather than in the bottom, and again your test error is too high. So you can see that test error will look like this, and you can find the optimal learning rate using cross-validation as before. But now I wanted to kind of see, so this is standard gradient descent. Basically, effectively just says, rather than calculating, and we're still talking about linear regression here, so rather than kind of calculating the analytical solution, I can also just calculate the gradient and then kind of go down step by step in the loss function by choosing the path of kind of steepest descent here, which is exactly what this equation does, and then I keep on updating. So this is the basic intuition. What I wanted to talk about now is actually how this relates to kind of what is known as backpropagation. So let's just maybe write out some of this expression here, and let's just maybe rather than W use the kind of A as we used before, so we don't have the mess up in notation here. So we had something like the total loss, which was also called G. So we have G, and let's just use A rather than omega. This is just the loss here. And this expression is basically given by, so I had here a 1 over n, and there also was an additional factor of 2 in the previous expression. And then in vector notation, it would just be y vector minus f of x transpose times y vector minus f of x here, which is the same as 1 over n times the sum over I times a half, and then I have yi minus f of xi squared, which is exactly what we had basically here. If I take this expression and if I take this expression, plug them in, and I call this omega A because this is what we prefer, then I get exactly this expression here. So I just shown that what we had on the previous slide is equal to that. That's exactly what we looked at last week when we looked at linear regression. We didn't use this prefactor here, but it doesn't matter whether I optimize the loss, whether I have this prefactor or not. As I mentioned, we only needed to be able to interpret this thing here as an average rather than a sum, and the two will just cancel if I differentiate. So let's just go back and see what happens if I differentiate this thing. This is what we did last week already. We took the loss function, we differentiated it, and besides this factor of 2 here, I will get the 1 over 2n, and then from the differentiation I will get basically, I can do the chain rule as well, and let's just do chain rule now rather than kind of summing it up as we did before and then calculating the differentiation of each term. Let's just say what I have there is something squared. So I know something squared differentiated will be 2 times that thing times the inner derivatives. This is just the chain rule of differentiation. So I will have here effectively y minus f of x, which will be kind of the outer derivative, and I get effectively down a factor of 2, so 2 times this would be the outer derivative, and now I get the inner derivative, which will basically give me minus df by dA transpose, if I like it to write like this. So now we see the 2 cancels, which was exactly the reason why the 2 was introduced here in the first place. So just for you to remember what this is, so this would be here the kind of outer, and this was the kind of inner derivative if I use the chain rule here. I'm just using chain rule of differentiation. So I have the outer derivative and the inner, where the 2 actually belongs to the outer and the minus belongs to the inner. But those things aside, I have outer derivatives and inner derivatives. I'm using the chain rule here. And then actually kind of just to write this out in terms of what we had last week. So obviously this thing I can write out further. So I know that so the f by dA is just x, because I have that f of x is equal to x times a. This is why kind of df by dA is just x. So if I write it out, I would get like 1 minus n x transpose times y minus x a here. This is what I would get if I write it all out. And now we see actually if we kind of set this equal to 0 like we did last week. Last week we wanted to find the global solution by taking the derivative, setting it equal to 0 and solving for it. And I will see if I would set this thing equal to 0, then I would get the same solution as before, because I would get something like A equal to x transpose x inverse x transpose y, which is exactly what we had before. If I take this derivative, set it equal to 0, solve for A, I will get exactly the solution that I had last week. But the idea here is not to do the analytical solution. We could do here for linear regression, but we can't do any more later for neural networks. So let's just see how we do in general. So in general, I will do this gradient descent here, and I will compute the gradient here, and then kind of I will go down in the direction of steepest descent. And the problem is usually how to calculate the gradient in the best way. Here I see it, the gradient is just this expression here. Let me choose a different color. The gradient is just this expression here, which is equal to this expression here. So in practice, I can just do it's just matrix multiplications here. I take y vector minus x times a, which is another vector, I get a vector, then I have x transpose, the matrix, I multiply it by a vector, and I get again a vector here, which is what it should be, because the result should be a vector of length, of the same length as my coefficients a, basically, which is p plus 1. So this is exactly how it works, and then I have found this vector here. So this is kind of dimension p plus 1. This is the size of this thing. It's a p plus 1 dimensional vector here. And once I have this vector, which I just obtained by doing this linear algebra here, I can now plug it into this relation, and I can compute the kind of gradient descent now, where I get my new weight, or the new a, equal to, and this is not the a index from the vector, it's a from the iteration. Let's just maybe put it up to be less confusing. So this is, I'm having a vector, and I'm now kind of choosing a new a vector, which is equal to the old a vector minus eta times this differentiation d of g by dA. So here we already see that this is obviously a vector of dimension p plus 1, this one as well, and this one should better also be a vector of dimension p plus 1, otherwise I couldn't be adding or subtracting them. And you can see exactly that's what it is, because this is a vector of dimension p plus 1, this is a vector as well. Now I multiply it by x, so I get a vector of length n. Y is also a vector of length n, but then if I multiply it by transpose, which is of dimensions basically p plus 1 times n, now we get a vector which is of length p plus 1, exactly as it should be. So this is what we see. Each of the gradient computation is just some linear algebra which is happening behind the scenes. And this is why it's important to be able to do the linear algebra efficiently. But this is not what I want to talk to you about. What I really wanted to show you is there's another interpretation of that thing. What I can do, and that's why I left some space in the middle here, this is obviously just the output of this function here. Or, no, sorry, I mean, f of x is just the output, and if I take f of x, which is the output, f is just the output, and then I kind of subtract it from the true value, I will actually get the error of my model. And now what I have here, this is kind of, so this is the inner derivative, df of dA. It's basically telling me what is the influence each of these coefficients a has on the output of the function f, which is kind of, you like, so influence of a on f, basically. I hope you can read it. So what I'm really doing, if I think about this picture here, I'm having some data here, which is this matrix X transpose. I'm taking this data, I'm kind of pushing it through the graph, and I'm getting an output here. This is sometimes called a forward pass. So I'm taking the data, pushing it through the graph, I'm getting the output here. Now comparing the output against the true value, and I'm getting the error here, this term. So now I'm getting the error. Now what I'm doing, I'm taking this error and this multiplication by the other term, I can think of it as a backward pass. Now I'm kind of propagating this backwards, because what exactly this term does here, df by dA is just the influence of A on the output of F. And it could be, for example, that, this here could have a very high value. This first one means that this edge here has a very big influence on the final value here. Effectively, if I increase this, then it will have the most effect on increasing F, basically. This is what the differentiation means. But it means effectively, once I do the forward pass, I get the output, then I calculate the error, I will basically see that my model was wrong by the error, basically. For example, my model predicts 5, but the true value was 4, effectively. So here comes out 5, the true value was 4, so I get an error of 1, basically. But now I can go backward and say, who was responsible for this error of 1? And effectively, if increasing this edge has the largest effect on increasing the output, correspondingly decreasing this one here has the largest impact on decreasing the output. It basically means that to get the output down from 5 to 4 to correct for the error, I have to decrease this first edge most, and then say the second edge less, and so on. And this is exactly what this term tells me. So I can see that actually calculating the gradient involves basically 2 components, which can be computed using some simple linear algebra, as I saw here. And effectively, the first one being the error, and the second one being this kind of influence of each of the weights on the output, basically. So first I and this has this interpretation of propagating the data through the graph, getting the error, then propagating it backwards and checking whose was most responsible for this, and kind of updating the weights accordingly. So now obviously if this guy here had the highest influence, he was the highest one responsible for being too high. So this is the one I have to be reducing most. And this is exactly what I do in this step here. When I do the gradient descent, I will get the largest gradient for this guy, and it will be the one which I will be decreasing most then. And this is the basic idea behind what is also known as backpropagation. So backpropagation, which you might have heard about, is just a very simple form of kind of interpreting the gradient computation using the chain rule. Obviously in this case I have just the one neural network, so there's just one step in the chain rule. But later on we will see for a generic neural network, it keeps on going like this. I just differentiate, then I differentiate further, and it's just kind of a longer chain in the chain rule. But all I'm doing here is I'm propagating through the data, get the output, calculate the error, and then propagate it backwards. And this is how backpropagation works, explained in the very simple case of linear regression here. And now I'm kind of just effectively writing down what I just said. So kind of to calculate the gradient when we differentiate with respect to the weights here, all we have to do is we compute this error, and then we kind of differentiate f with respect to the weights, which I also called a, and effectively see which of the contribution of these weights, which was the contribution of each of these weights to the error, which is given by the influence, and then I will basically update them accordingly when I do the gradient descent step. And this is effectively a very simplistic form of backpropagation, which is worthwhile to kind of highlight on a separate slide. It's effectively what I just said. So first thing, I pass through the data to get the error. This is the forward pass, and it corresponded to the outer derivative when I did the chain rule here. And now what I'm doing next is I kind of take this error and I propagate it backwards to the left using this backwards pass, and this is effectively what the inner derivative did when I looked at this expression here. This is exactly what this term, which is also the inner derivative, did. So I have the outer derivative, which is effectively my forward pass of the data, and then any of the inner derivatives will be my backward pass of the data, where I kind of update how much this error was influenced, and I'm kind of updating the terms accordingly. So this is a very basic idea of how backpropagation works, but effectively, even though we discussed it only for a linear regression model, this is exactly how any neural network is trained, only that the neural network has obviously different layers of neurons, and this backpropagation will be a bit more complicated. There will be more kind of sequences of chain rule, but the idea is basically the same. So now we have seen from linear regression we can already learn a lot about neural networks, and now we will see how we actually stack those neurons together to get larger neural networks. So that's what we will do next.